Let's wait for 2, 3 minutes. After that, I will start. Okay. Uh, so before starting this, let me introduce myself. I am Shujatra Bhattacharya, fourth year PhD student at Indian Institute of Science. So I'm working in at Center for Atmospheric and Oceanic Sciences uh, at IAC, and mostly my work is on atmospheric physics, particularly understanding the monsoons and other energetic aspects. So this is mathematical physics course, which is utilized in many fields, not only in physics, but in geophysics, in atmospheric physics, everywhere. So, so it's an interesting course. So I will try to give a simple explanation of whatever is being covered in each week, and we can solve some questions based on that, so that it is much more clear, and you can solve the assignment questions as well. Okay. So with this, let me just share the screen and start. I think I can now switch off the camera to starting. The network issues. Okay. So mostly in the week 1, which what I have seen in this particular course, uh, the concept of linear algebra is particularly being discussed. So, so this is week 1, mathematical physics second life. Okay. So the main things today which I will discuss is that the concepts of the linear algebra, like starting with vectors, then linear vector spaces, then you have dual vector space, which is important to understand the inner products. But before that, we will see the dot products or the vector scalar products. Okay. These things are there, and then inner products, just a so these dot products, inner products, all the same, but when you include the complex numbers, inner products are useful. Okay, once this is done, then we can go to linear dependence or independence. So that we can just see. And finally, the row reduction technique. And finally, the rank, how to calculate the rank of the matrix. All these things we will see in details. So I will slowly go ahead, and in between we can solve some questions. Uh, so that is the total plan for today. And there are assignments, of course. I think the first 2 weeks, two assignments has to be submitted in the next to next week Wednesday. I think something like that. So I can discuss those assignment questions after your assignment one and two are being already being checked. You will get the solution there. So after that we can discuss. But before that, whatever the concepts are being covered in the lectures, in the videos where you are following, and along with this, whatever the tutorial session is there. So there we will try to solve certain questions so that that will be helpful for your assignment question solving. Okay, so with this, let me just start now. Okay, so okay, so the starting point is that you start with vector. So in physics, we generally say that in a very simple language, what is a vector? Vector is nothing but any physical quantity which has a magnitude. Along with that, there must be a direction associated with it. Like we say, the acceleration is a vector. So, so acceleration. Then we have displacement, velocity. All these things are basic examples of vectors which associates direction with it. Okay, so acceleration, displacement, velocity. However, their magnitude, like speed, is a scalar quantity. Similarly, distance and all these things. Okay, so these are scales which only deals with the magnitudes of the quantity. Okay, but in linear algebra, this vector definition is not only limited to, so the vector definition is not only limited to your speed and direction kind of a thing, but it has more to it. So we will see all those things, that there must be some addition criteria, there is a scalar multiplication that it should follow. Okay, so all these things we will try to look. So mathematically, it has some more properties, right? Those properties we will see. For example, it should satisfy, yeah, it should satisfy the addition as well as scalar multiplication. Okay, so these things we will see. So, for example, let us take the example of addition. So, we all know, those who are coming from the physics, of course, in class 12 also, in the starting UG courses, you know that in the physics there are two ways of adding vectors. So one is the simple geometric approach, which we generally call as the triangle law of addition. So geometric approach. Yeah. So the geometric approach means we are actually dealing with the triangle law of vector addition. I'm writing triangle law of addition because we are dealing with the vectors here only. So what does it say? So suppose that you have two vectors. Let's say this is A, some vector, and this is some B vector. Then its resultant is this. Okay, so this is some vector C, which is the resultant vector. Thus that C is equal to A plus B. So in the triangle of vector addition, the most important thing is that the two vectors which are getting added, they are not a co-initial. It is not a co-initial kind of a vector. Co-initial means that from this point two vectors are originating. Okay, we can of course take this vector and shift it here. That we will do in the parallelogram law of vector addition. This is another way of method of doing. Ultimately, all the methods will give you the same resultant vectors. Okay, so this is one of the methods. This is the triangle law of vector addition, where this is the resultant vector. Okay, another is what is called the algebraic approach. So there, what we do is that we try to calculate using the components. So you have again these two vectors, say A and another vector is B, and we know that there is a property of this vector is that we can shift parallel, this vector parallel. So what I will do is that I will shift this B vector parallelly so that it becomes some kind of a coincident vector. So this now becomes this. Okay, so this is now A, this is the same B. I have just shifted parallelly. Okay, now there is a resultant vector. So what we can do is that we can do like this. There's a parallelogram kind of thing, and we just join this. So this is kind of following the parallelogram law of vector addition. Or what you can do is that take these vectors and try to write it in terms of the x coordinate, y coordinate, and z coordinate, the three mutually orthogonal coordinates, and try to write it down. So let us consider there are two coordinate axes because this is the plane. So we can have suppose Cx, the resultant vector is suppose C, which we have written here. So its x component is nothing but x component of A plus x component of B. Similarly, there is a Cy which is Ay plus B. So this is called the component wise addition. Component wise addition. And we know that these components, AX, BX, these are all scalar. They are not vectors. When you additionally give a direction of unit vector, I hat, I cap, j cap, k cap, whatever you wanted to give, or ex cap, uy cap, same, ez cap, then you get it as a vector. Otherwise, components, the value of the component is a scalar quantity. Okay, these are very basic things. Okay, some more properties are there in case of vector addition, uh, which must be taken into account, particularly for this linear algebra part. So one is that addition of vectors, of course, we are dealing with vectors. Addition shows commutative nature. So we all know what is a commutative nature means. Simple is that if you are adding a plus b, whatever be the result is same as adding b plus a. Okay, it will give you the same thing. So a plus b vector is equal to b plus a. Okay, this is the commutative nature. Next is that it also follows the associative nature. Okay, associative. Okay, so this it also follows. But for associative nature, you need three vectors because that is how you do. So what is that? Okay. So what we can do in this associative nature is that you have suppose three vectors A, B, and C. Just add two together and then write like this. This is exactly similar to A plus B plus C. Okay, in one parenthesis. So this is called the associative nature. We have seen in the real numbers in very early schools, real numbers where this kind of properties we generally have used. Same thing can be applied for this vector. Okay, so these two important nature, the vector addition follows. One is the commutative nature, another is the associative nature. And we have seen two kinds of addition of vectors. One is the component-wise addition, another is the just use the geometric approach of triangles law of vector addition. Okay, so now let's move towards the scalar multiplication. Scalar multiplication. This is another property of the vectors after addition. So let us consider, for this case, let us consider a scalar quantity. Let's say that is alpha. This is some kind of a scalar quantity. It can be real as well as complex. Okay. But right now, let us focus on the real components. We will see what happens with the complex component. We have to wait for some time. Okay. So let us consider this alpha is a scalar quantity, and this alpha times A is nothing but a scalar multiplication with the original vector. So what it does, it actually scales the actual vector. So it scales the original vector A. So not only does it can change the magnitude, but direction also it can change. It has a control on both the direction as well as magnitude. For example, if you have your alpha is equal to say -1, it is just the opposite of A vector. So suppose your vector is in this direction, same magnitude, the direction will change. So it controls both the magnitude as well as direction. Magnitude here it will not change because I have taken the value of the scalar quantity as 1. But if you take 2, 3, 4, so the magnitudes will also change. Right. So this is one of the important things. So alpha less than 0 will also change the direction. Not only it change the magnitude, of course it will change the magnitude, but it will change the direction as well. Okay. Basic thing. Okay. Fine. Once we have dealt with this vector addition and scalar multiplication, which the vector follows in case of mathematical nature of the vector. So what next is that some notation that how we can write, even symbolically write the vectors. Okay. So vectors can be written in ket notation. So there is a ket notation and there is a bra notation. So together it becomes bracket kind of a thing. So this is the ket notation. When we come to the inner product or the dual space, there you will find that the bra notation is being used. But now for a vector quantity, we will use the ket notation. So what is this? This is the ket notation, which denotes nothing but a vector, like this, x vector. So x, this ket notation is equal to x vector. That's all. Okay. So this is one of the notations with which you can write the vectors. Fine. So now let's see what properties using this vector notation what we have used. Let us list down all the properties of which the vector follows. Okay. So these are the properties. We have seen some properties, but there are many others. Okay, so let's list down all those properties. First is we have already seen, so I'm just writing this is the commutative nature. So you have what is this commutative nature means? Suppose you have vector x1, another vector say x2. This, if you add, this is same as x2 plus x1. Okay, this is the commutative nature. A plus b is nothing but b plus a vector. Fine. And exponents were the vectors, of course, because we have already shown that. Next, associative. This is also I have shown. So associative nature, it follows three vectors are required. So your x1 plus x2, these two together, plus x3 is equal to, you can write x1 plus x2 plus x. This is how you can write the associative nature. Fine. Third is, if you multiply with the scalar quantity 1 with this x, it becomes x. It's nothing but known things. All these known things are being listed as a property in the vector space, in n vector. Okay. The fourth one is the associative law of multiplication. So let's see what is that law of multiplication. So let us consider alpha and beta as scalars. Okay, so your alpha times, suppose beta x, x is the vector here. If it is written like this, you can always write this as beta times alpha x. So you can multiply alpha first with the x or beta first with the x, then multiply by the other terms in this associative law of multiplication based on that. Okay, this is the fourth property. Fifth property is distributive law. Distributive law. This is with respect to addition of scalars. All right. So this, what does that mean? Again, alpha beta just go with scalars. Alpha plus beta times ket x, that is a vector, can be written as alpha times x plus beta times x. This we can write. Okay. Same thing, the sixth property, same thing, distributive law, but now it is with respect to the addition of the vector. Earlier it was with scalars, now it is with vector. So distributive law with respect to addition of vectors. Alright, so what we will do? So one scalar you take and you have two vectors now because you need vector addition, right? So these are the two vectors x and y. You multiply with alpha. So you can write this as alpha x plus alpha times y. This is how the distributive law is uh, written. Okay, so there is this six list of properties we have seen about the vectors, and we have used the ket notation of the vectors. Okay, so these six properties are important. Now, this from these six properties, we will take certain properties and try to define a linear vector space. So, what is a linear vector space? So, what is a vector space? As the name, you can understand that it is nothing but a set of large number of vectors which will follow certain properties. So there is a set of vectors which will follow certain properties. That is nothing but a linear vector space. That's all. So linear vector space, LVS we generally say. So let me write first. So linear vector space. Okay. So we generally call it as LVS, linear vector spaces. So it is what? It is a set of vectors because it's a space. The set of vectors will be there in that space. Okay. Now I can write this as S as say x1, x2. These are so many different vectors which will be there in that space. And say suppose xn and many others. Okay. Lots of vectors will be there in this, but these vectors should satisfy certain properties. Okay, so this should satisfy the following properties. Okay, this will follow certain properties. First is we will do certain questions also based on that, and that will be much more clear. Okay, so one is the closure under vector addition. So how will we mathematically write it? So suppose you have a vector x1 which belongs to this linear vector space S. Okay, x1 is a vector which belongs to the linear vector space S. Similarly, let us say x2 is another vector which also coming from this same set of vector, that is the linear vector space, some space. It is coming from that. Okay. Closure under vector addition says that if you add these two vectors, say x1 plus x2, that should also belong to this space S. Okay. So x1 plus x2 should also belong to this set S, from where the x1 and x2 are coming from. So this is the closure under the vector addition. Okay. So the same nature which the x1 and the x2 follows, x1 plus x2 should also follow the same nature. That's all. Number one property is this. Second is the closure. As you can understand, one is vector addition, then there will be definitely a scalar multiplication. So closure under scalar multiplication. Okay, closure under scalar multiplication. And for that, what you require? You need a alpha, which is a scalar quantity. We define alpha as a scalar quantity. It can be real, it can be complex, anything. Okay, it's a scalar quantity. That's all. Important thing is that one vector should be there. So your x is a vector which is coming from the sample set S. From space S. Thing is that your alpha times x, the scalar multiplication closure will be possible only when the scalar which we have defined times x will always should satisfy or should belong to this set S from where the x is belonging. Okay. So again, the nature which the x vector follows, same nature should be followed by alpha times. Okay. So this is the closure under the scalar multiplication. We'll see the examples definitely. Okay. The third one is your existence of a null vector. Null vector is the zero vector. Okay. So existence of null vector. Okay. So this is nothing but this. This is called a zero vector. You can null vector is fine, zero vector is also fine. All elements should be zero of that vector. Okay. So what it essentially says that suppose x is coming from this sample space S. Now now what happens is that now if you just add this x with the zero vector, well, we all know if you add in any number also with a zero value, what it will give? The same number. A similar thing is happening in case of the vector spaces. Okay, so x plus this null vector, following the commutative nature, you can write this also. This should be equal to your original x vector. That's all. Because this zero vector will always consist of the zero element. Okay, so ultimately, each element if you add of the vector as well as the null vector, it will give you the original vector x. Okay, this zero vector should also lie in that particular x space. Okay, and number four is your existence of inverse or additive inverse, I will say. Existence of inverse. And this inverse should be the additive inverse. Okay, just additive inverse. Additive inverse. Okay, fine. So how we can write this? So suppose you have a vector x belonging to S. Fine. X is a vector which is coming from the sample set S, where so many vectors are there. It should. Let us consider that it has an additive inverse. Additive inverse vector. Remember, additive inverse vector as say x inverse. Okay, which should also belong to this S, such that your x plus your x inverse, what it should be? It should be equal to the null vector 0. Fine. So this should happen. Similarly, that if you have a scalar quantity, say 2, and there must be So it is showing that there must be another scalar that is minus 2 such that 2 plus minus 2 becomes equal to 0. That's the thing. That's the thing which we are talking about. Okay. So this is what your vector space represents. Say set of real numbers if you have. Okay. So there 2 minus 2 is 0. 1 minus 1 is 0. So all these things exist. Okay. So these four properties, this should be followed in order to say that a particular space is a vector space. Okay. So what we are trying to deal with here is that suppose I am saying that this S is a set of several vectors. I want to confirm that this S is a vector space or not. To confirm that this S is a vector space which consists of several vectors, we try to do certain exercises. And these are the four properties we should check. Once these four properties are followed, then we can say that with confidence that this S is a vector space. That's the thing. That's the point. Okay. So let us do some questions. Then it will be slowly getting clear. Okay. So let's see one question. So suppose you have been given that determine. So this is the question. This is how the question is being given. So determine whether the given set of vectors maybe is a vector space. So we need to confirm that whether those given set of vectors are vector space or not. So what is given? So it is like this. So this is the set which consists of two elements, the A and B. These are two elements which are there, which should belong to R square. That is, it is the real space with square because there are two elements. Okay, such that B is equal to 3A plus 1. Okay, so you have two elements. Okay, you can write this as like this: A, B. Okay, like a matrix kind of a thing. Okay, so this will be a 2 by 1, two rows, one column. This is a vector. Okay. This is how in linear algebra we define a vector. Okay, so this is a 2 by 1 matrix. Remember, in case of vectors, always remember that it will be a kind of a column vector. But sometimes for the vector space, we generally go for a matrix also. Okay, but generally, vector is represented as a column or a row vector. Okay, but let us, for the time being, say that this is the question which is being given, where this A and B has a relationship. This B is equal to 3A plus 1, and it belongs to R square. Why R square? Because there are two elements here. Both are coming from the real space. Okay, this is the situation. I have to state that whether this S follows all these four properties or not. If they are following four properties, great. Then it is a vector space. Okay, this is what we have to do. Fine. So to start with the question, use this relationship. This is important. Okay. So now what we will do? Suppose this is A. Okay. The second element B. Let us write it as 3A plus 1. Okay. So now this is the generalized vector. Okay. So every time it can be A1, it can be B can be written as some A, 3A1 plus 1. Okay. So let us see. Let us define now. Okay, so the first property is what? The closure under addition, right? So closure property. See, in the closure property, what we can do is that, see, this is x1. Okay, let x1 be defined like this: a1 and b1. Okay, let us write this b1. Okay, what we can write here is that a1, but b1 is what? 3a1 plus 1, correct? Based on this particular relation, we can write like this. Fine. Now, let us say another vector x2, which is having, let's say, elements a2 and b2, which we can write as a2, the first element, and the second element by the relationship, we can write it as a2 plus 1. Okay, you just add it. First, let us add it. So, what it will give? It will give you See, this is A1, 3A1 plus 1. Just component wise add. Okay, A2, sorry, this is a plus sign. 3A2 plus 1. So this element will be getting added to this element will be getting added to this. Simple. So what will be the first element? A1 plus A2. What will be the second element? 3A1 plus 1 plus 3A2 plus 1. Correct? Fine. So what we can write? This is A1 plus A2. And what about the second element? 3A1 plus A2 plus 2. Correct? This is what we are getting. Great. Now, I combine this A1 plus A2 and say that, okay, let us say that this is C. Okay. So let A1 plus A2 is equal to C. Then what we can write about this? So what is the vector? So this is C. See this A1 plus A2 is here also. It will be 3C but plus 2. Alright. This is what you have. Now C and 3C plus 2. These are the two elements we are getting. Great. But tell me now, what about the x vector? What about the x1 vector? See, the x1 vector is A1, whatever the element is present in the first row, same element here is present, but with that plus 1 is there. Similarly, next to A2, 3A2 plus 1 is there. But what about x1 plus x2? See, C is there here, 3C is also there, but there is no 1 here. It must be 1 to satisfy the coming from the same set, right? But it is not following the same nature. It is 3C plus 2. It is not 3C plus 1. Therefore, it is not belonging to the state S. And there, the closure of addition is invalid. Okay. So this closure of addition, vector addition, is invalid. Why is it invalid? Because you have to look for this. See, when you have defined this x1, it has a1 and 3a1 plus 1. x2, a2 plus a2 and 3a2 plus 1. But when you are adding, it should be c and 3c plus 1. But you are getting what? 3c plus 2. So that means it is not following the same nature, or it is not following the same relationship base. Okay? 3a plus 1 is coming from this relationship. That is not being followed. That means it is not belonging to this vector space or this set. And hence, we cannot say that this is a valid vector space. From here only, we can say that it is not a valid vector space. Further, you can do definitely. There is no problem in that. But let us say, let's do for the existence of the third property. Okay, let's say the existence. Let us check. We have already seen that it is not following a vector space, but let us see the existence of the zero null vector, whether it is present or not. We can write it or not. So you have vector x, suppose, which is having a and 3a plus 1. This is what the which is coming from the R square. Okay, okay, this is not S, or you can say that it is not belonging to R square. Fine. You have this now. Fine. Now, what you do is that what is the condition that your zero, this null vector should exist. Correct. So if null vector should exist, then each and every element should be zero. See, you can have your a zero, fine, but what about the second element? 3 into 0 plus 1. It will always come out to be 1. If a is 0, the second element b will always come out to be 1. So this is also not possible. Therefore, each and every property, if you look at, it will show that it is not possible. Okay. So this is therefore we can write finally that your S is not a linear vector space. All right. So this is what this particular question is, that it is not a linear vector space. Fine. Okay. Another important thing that I wanted to show is that this closure under addition, closure under scalar multiplication, you don't need to separate it out. You can include it here only. Okay. So let me just discuss this. The closure under vector addition and scalar multiplication can be written together or checked together. sorry, scalar multiplication can be kept together. How will you do that? Simple. So you have suppose alpha and beta as scalars, okay? And your x1 and x2 are vectors, right? These are two vectors. So what you will do is that you just do this alpha x1 plus beta x2. Check this whether it is belonging to the sample space S or not. If these are coming from S, okay. This will also tell you that what will be the whether it is closed or not. Okay. So this is another way you can check. We can see in the next example maybe. So there is a second example. Let us follow this. Okay. So the second question is same whether a set V is a vector space or not. Okay. So you have same two elements again, x1, x2, which of course belong to R square, but following a relation 2x1 plus 3x2 equals 0. This is the expression you have. Okay. It should follow this particular relationship. That's all. Okay. So let us say that this is a vector A. Let's see this A, which consists of x1 and x2. And based on this relation, you can say that x2 is nothing but minus 2 by 3 x1, right? Minus 3, yes. X2 is minus 2 by 3 x1. So I can rewrite A as this. So this is x1 and this is minus 2 by 3 x1. Alright. Similarly, this also belongs to this R square, definitely. What about B? B is also coming from this vector space B. What about B? B is, let's see, the same thing, but x1 dash. Let's see, this is minus 2 by 3 x1 dash. Some different elements. Okay, this is also coming from this same B, following the 10 conditions of B. Fine. Now, let us see the closure property, which includes both addition and multiplication. So, this is alpha and beta scalars. Let us say, means define it. So, you have alpha A plus beta times B. All right. So let's do it. What it will be? So alpha times A is x1 and minus 2 by 3 x1 and plus beta B, which is x1 dash minus 2 by 3 x1 dash. All right. So if you do this, finally what you will get? The first element will be alpha x1 plus beta x1 dash. Right. Second will be minus alpha 2 by 3 x1 minus 2 by 3 beta x1 dash. Fine. So we can rewrite it properly that alpha x1 plus beta x1 dash and your minus 2 by 3 can be taken common. Again, you can write alpha x1 plus beta x1 dash. Okay. This is the second element. So you can see that you can rewrite this as some C vector, not C vector or C element. And look at this. This is also the same C. So what we can write is that it is finally coming out to be C and minus 2 by 3 C, which is fine, which is following the same nature as A and B. See, this same nature. So if it is following the same nature, so it is closed. It is closed under addition as well as scalar multiplication. Okay, this is done. Second is your existence of null vector. Okay, existence of null vector. So you can just show that. Okay, you can see that if C is 0, minus 2 by 3, C is also 0. So it's fine, exists, no doubt about that. Okay, and so null vector exists. You can see it exists. Just put any x1 dash equal to 0, then minus 2 by 3 x1 dash is also 0. Okay, so null vector exists. Third is your inverse should exist, that is additive inverse existence. So these are you can just check very. Smoothly because these are all online questions and MCQ type questions. So you don't need to solve everything. If you want to, you can do. There is no problem. So how to do it? How to calculate the additive inverse? So you just subtract the actual vector, the A, from the zero vector, the null vector. Then only you will get the additive inverse. So it will be nothing but minus x1 and this will be 2 by 3 x1. That's all. So there is an existence. Existence. Okay, so this proves that this V is a vector space. So V is a valid linear vector space. That's all. So this is how the question has to be tackled. One, you have to check certain properties, particularly the vector addition and the scalar multiplication. Those two has to be satisfied. After that, you go for existence of null vector or inverse. That is up to you. Okay. Another important thing to note, it's star mark, which will be helpful for your assignment questions also. That set of complex valued functions. Here we are dealing with the real valued function. We have always written it in terms of r squared. These are real valued function, but set of complex valued functions, okay, also forms linear vector space. Okay? This is one point which I wanted to uh, highlight. Okay, so these are the some questions we have seen about the linear vector spaces. How we can say that really a particular set of vectors is a vector space or not. Okay, now let us quickly go to an important some important things like first is that you have there is a uniqueness. Okay, there is a uniqueness of null vector and inverse. So uniqueness of null vector, it is proved very easy. Okay, very easy. So let's assume. So if you have a set of vectors which is forming a vector space, and we know that there must be a zero vector, a null vector, which is existing in that particular vector space. Right? Question is that is there another null vector? So can it be possible that there are two null vectors existing in a vector space? So we are saying that no, only one. Okay. So let's assume how to prove that. So let's assume that there is a second null vector. Okay. Let us first assume that the wrong part. Okay. Second null vector, and which is nothing but the zero dash. And original null vector, original null vector is zero, suppose. Okay. Just use the commutative nature of the addition of two vectors. So 0 dash plus 0. Consider this as a vector, right? So 0 dash plus 0 will give you what? 0 dash. And see, this thing can also be written as like this 0 plus 0 dash. The commutative nature. This will give you what? 0. So ultimately what? If these two are equal, if these two are same, if these two are same, the commutative nature, then what? 0 dash should be equal to 0. So 0 dash plus 0 must be 0 dash. But if you write this in a commutative nature, then it will be 0 plus 0 dash, which will be nothing but 0. Now they are same, right? So this represents that there is a unique null vector. Only one null vector should exist in the vector space. There is no two null vectors. Similarly, there is a uniqueness of the additive inverse of additive inverse. Right? So again, in the same way we will go. Okay, let us consider that there are two additive inverse. So consider that two additive inverse exists. Additive inverses exist for a particular vector. For a particular vector. Remember, this is important for a particular vector because A vector space consists of several vectors, right? And each vector has a particular additive inverse. So for a particular vector, there are two additive inverses. What are those? One is the x inverse, the original one, and another is x inverse dash, suppose. Okay, and both belonging to say some s vector space. I know that x, the actual vector, suppose this is the original vector. I can write that this x plus x inverse should be equal to the null vector. This is the rule, this is the nature. Okay. So what I do is that now you use the associative nature. See, earlier we were using this for the null vector one, we have used the commutative nature. Here we use the associative nature. So what we will do is that we add with the x inverse dash. So this is how we write x inverse plus your x inverse dash is equal to 0 plus x inverse dash, right? This we can write just adding to the right of this. Fine. Now, what we can write here is that this x, all right, x plus now this x inverse dash plus x inverse must be equal to 0 plus this x inverse dash. All right. So now this, if this is a true, I would say it is the inverse. So this should be also 0 plus x inverse must be equal to 0 plus x inverse dash. Right? So what is this? 0 plus x inverse is the vector itself. What is this 0 plus x inverse? Again, should be the vector itself. So finally, x inverse should be equal to x inverse dash. There must not be two additive inverse for a particular vector. So one unique additive inverse for a particular vector. Okay, that's all. These are the two important uh, proofs. Now, we will quickly jump to the vector scalar product because too many things have been covered in the first content, week one. So, let's see how much we can go. Okay, so let's go to the uh, what you call as the vector scalar product, or we generally call it as a dot product. The dot. So what it means is that you have two vectors, suppose. Finally, if you do a scalar multiplication or scalar product, then final the answer is a scalar. It's not a vector. Or so how to start with this? Okay, what is the general expression first? Let us say two vectors A dotted with B. These are two vectors. The final answer is scalar quantity, which is generally given as this AB cos theta. This which we have seen in the work done kind of a thing. Yeah, so force into displacement of F S cos theta. Right. So all these things we have seen, even in the electric field, magnetic field, all those things where we have seen this kind of a thing. This dot product exists. Okay. So to prove this, actually, you need law of cosines. I just wanted to show this because I think in the content which is given there, there is something uh, mistakenly written. I don't know, but let me just quickly show you. Okay, so suppose this is a triangle. Suppose this is A. Okay, this is A. Suppose this is B and this is C. Okay, and this is some theta. This is a vector AB, BC, and CA. Okay, and the magnitude of this AB is A, this is B, and this is C. Finally, from the law of cosines, this is completely mathematical law of cosines. I just write it. C square is equal to, using trigonometry, you can easily derive it. So it is c square is equal to a square plus b square minus 2ab cos theta. If this is theta, okay. If this is alpha, this is gamma, then you can write all others. So wherever this angle is, the opposite side square, b square, is equal to a square plus c square minus 2ac cos alpha. Similarly, a square, which is this one, so it will be b square plus c square minus 2b into c cos gamma. This is how the law of cosines using the sides and the angles of the triangle we can write. Okay. The important thing is that if you consider this as a vector now, then what happens? So you have this vector AB, B, BC, and this is CA, magnitudes A, B, and C. This is suppose theta. We want AB dot BC. Okay, for the time being, we want AB dot BC. But using triangle law of vector addition, what we can say? We say that AC is nothing but AB plus BC. Correct? This we can say. See, these are two vectors and this is the resultant vector. Alright? So this we can say AC is the resultant vector. Remember, this is not the direction, AC is this direction. Just remember this. I have written AC, not CA. Fine. So this is the coming from the triangle law of vector addition. Fine. Now what we'll do is that we just dot product these two. So AB plus BC dot again AB plus BC. This is the dot product we are doing. On the right hand side, we are writing AC dot AC. Same thing. Both sides just multiply. What it will come? It will be AB dot AB, these two, plus BC dot BC, the second terms, and you have 2AB dot BC. Correct? This is what you will get. Right hand side, AC dot AC, not change. Fine. Now, these are two things which are being multiplied. So what we will do is that let us keep 2AB dot BC on the left hand side, and this AC dot AC can be written as mod AC square. Similarly, this will go to the right hand side as minus mod AB square. This also will go minus mod BC square, right? This will come like this. Now, what is this AB? Sorry, this AC square. AC square is this one, right? So it will be C square. This is C square minus what is AB? A square. What is minus BC? B square. Right? Look at this. C square minus A square minus B square. So what is that? Minus 2AB cos theta. So can I write this as minus 2AB cos theta? AB cos theta. Or minus 2. A is what? A is what? AB. The vector AB. B is what? BC and cos theta. What about in the right hand side? Sorry, left hand side is AB dot BC. 2 can be cancelled. What you are getting is AB dot BC is equal to mod of AB into mod of BC into cos theta with a negative sign. This negative sign is not mentioned in the week 1 content. Somewhere I have seen it is not mentioned. But this negative sign is important. It is not there in the week 1 content, but here it should be important. Why it is important, I'll tell you. Remember, in the dot product, if you have a vector A like this and a vector B like this, and there is a theta in between them, then only you can write A dot B is equal to mod A mod B cos theta. That means that now these are coincident vector. Remember, this is coincident vector. Or sorry, co-initial vector. Co-initial vector. That is, it is originating, those vectors are originating from a common point. Okay, these are co-initial vectors. But look at A, B, and B, C here. This is here, AB vector is this and BC vector is this. So what I have to do to make it coinitial, and this angle is theta actually. So this is A, B, this is B, C. So what do you do? You have to parallelly shift it, or in the forward direction, you have to shift this vector to make it like this. Now, if you do this, this is theta, this will be something else. Okay, this angle becomes something different. Okay, so that you have to be careful. So this will be coming out to be about 180 minus theta kind of a thing. So based on that, you have to check the signs and things. Okay, so this is important. So just remember this coincident kind of a vectors. So finally, you can say that if you have two vectors, say your A and this is your B and this is theta, then you can write A dot B is equal to mod A mod B cos theta. This is your dot product. Just no need to worry about any other things. Okay. And yeah, so this is the main thing. Finally, in terms of component wise, A dot B can be written as AX BX plus AY BY plus AZ BZ if you have that IJK vector. I suppose, okay, this is J and this is. So in that way, you can just do this. Okay. Also, if A dot B is equal to 0, then the theta is actually 90 degrees. Correct? Because this is what is coming from that. All right. So these are important things. And yes, so fine. All right. Now, what else? Okay. Some properties of standard uh, properties, yeah, of scalar product. For a legitimate scalar product, it must follow certain properties. One is that, of course, A dot B, that is a commutative one, is equal to B dot A. This is important because one of the questions I have seen in the assignment is based on this. Second is A dot A is your greater than equal to 0 because this will be nothing but mod A square, should be always be greater than equal to 0. Third is that A dot a null vector is always 0, scalar, of course. Okay, and the fourth is that A dot some alpha is scalar, suppose B plus beta C is nothing but alpha times A dot B plus beta times A dot C. All right, so this is the distributive nature. So these four properties a legitimate scalar product should follow. Distributive property. Okay, so this is important. This has some question I think in the assignment. Right. So yeah, these are fine, I guess. Yeah, I don't think anything else is there. Yeah, it's fine. So this is final. Next, we will go to the inner product, and for the inner product, we need a dual vector space. The concept of dual vector space. Okay, so this is the concept of dual vector space. Okay, so now you have x. Yeah, suppose x, y, and so on several. There are many be the actual vectors. We have seen that we have used the ket notation for writing the vectors in a particular linear vector space. Vectors in a linear vector space. So V is the linear vector space. Okay. There is a corresponding dual vector space. What does that say? So there is a dual vector space in which in which we we write those in bra notation, that is this. See, this is the cake notation, this is now the bra notation. So x, this is y, and so on. So corresponding to each x vector, one of the vectors, there is a corresponding another. I would not say this is a vector, but this is a kind of a transformation. This is not a vector. Okay, so this is a kind of a transformation. I will discuss it in details that what is actually happening. Okay, so this is a kind of a transformation, and this is a linear transformation. So let me write first. So every the same thing which I have shown, just maybe I'm writing it. So every ket vector x in V for every I would say, for every ket vector x in V, there is a transformation vector. You will understand it. I will have some examples also. So this is dry in dual. Okay. So what is happening for a particular vector x, which is denoted by a kit notation in the linear vector space, which we have seen so far, there is a transformation vector. It is a linear transformation essentially. So there is a transformation vector which is denoted by bra x by this sign in dual space. Okay. So this is the important part. The basic difference between this kit and bra notation is that for the kit notation, when you have written the scalar multiplication, say alpha times x is a vector, alpha is a scalar. Okay, so alpha times x. This is the kit notation. This is the original vector. Oh, sorry, no, I'm writing it wrongly. Wait. So alpha times x. This is the vector. This can be written as we have seen alpha times. But if you have to write it in bra notation, alpha times x, the same thing, since it is a transformation, it becomes alpha star x. What is this alpha star? Is nothing but a complex conjugate. See, when it is a real quantity, you don't need inner product. You can go ahead with the dot products. Okay, all these real quantities, you can go ahead with the dot product. You don't need real product, this inner product. So inner product will come, which is nothing but a dot product, but it includes, it's a more generalized way where you can include both the real as well as complex space elements. Okay, so this is the complex conjugate of this scalar quantity. So we are assuming that alpha can be scalar, sorry, scalar of course from real or complex field. So if it is a complex number or a complex scalar, then this complex conjugate will be important. Okay, so this is the basic difference between a get notation and a bra notation, which we must know. Okay, so I would say if you further want to discuss about this notation, this is nothing but a kind of a linear transformation. It's a linear transformation in V, suppose which is R, or I would say V to R. So this is already in V space and it is going to a R space. Okay, similarly, or complex space we can say. Fine. So this is okay. Now the original thing is that let us consider the inner product. Okay, inner product, which is nothing but a generalized. It is a generalized uh, form of scalar product. Okay, it's a generalized form of scalar product. So you have a vector scalar product or a dot product. At the same time, there is an inner product. Inner product is consisting of a kind of a generalized scalar product, which is coming from both, which includes both the real as well as the complex fields. Okay, so how we can write this is this. So x, and suppose this is a y plus z, I can write this as x y plus x z. Okay, similarly, x times cy. See, this part is a vector and this is the linear transformation. So this is the transformation, I would say transformation operator, and this is the vector. All right. So this will be simple. C x y. So this is the inner product. So inner product of x comma y. So here x and y, the state can come from real as well as complex. Earlier, in case of dot product, when we are not using this inner product, there it has to be real. Here it is both real as well as complex. So inner product is nothing but the vector scalar product, but which consists of or which includes both the real space as well as the complex space. That is the most important part. Okay, but the problem is that if you have c times x of y, this is not equal to c xy. Remember, because this c is multiplied with the x in the bra kind of a notation. It is in the transformation. So what it is actually C star, the complex conjugate X with Y. Okay, this is the basic definition. Fine. So if you have to further write as an example, so let vector space B is coming from Rn. So there are n elements in vectors in this vector space. Suppose x1 is a vector which can be written like this, okay, and it is belonging to Rn. N elements will be there for a particular vector. Okay, so now you have a vector x1. This is the linear transformation as I was discussing. This is important. Rn to R1. Why R1? Because this operation will do a kind of a dot product, and dot product's result is what? Is a scalar. So scalar should be R1, right? It should be one value, which is scalar. Okay, so this is what is important. And what it will do? It will be just like this. So x1, x2, so on up to xn. Or originally it will be nothing but x transpose. If it is real, then it is x transpose. If it is complex, it will be conjugate transpose, Hermitian kind of a. Okay, so this is what is important. So this is like nothing but a transpose. I can write like this x1, which is nothing but x1 transpose. So what is this x1 vector? X1 vector was like this. It's a column vector. I would say x11, say uh, 1, 2, so on up to x1n, because n element should be there coming from Rn. So this is how it is. Now x1, this bra notation where you are doing a linear transformation, it will be x1 transpose. This is how it can be written. Okay, and yes, so this is how it is. So this, now if you do like this, it will be, so x1, I can write like this also. It's fine. 1, 2, 1. So this is x11, x12, so on up to x1n times, you have to do this. X11, x12, so on. So you know that it will be finally what? It will be x11 square plus x12 square and so on up to x1n square. So it is nothing but the dot product. Correct? This is nothing but the dot. Because dot product, because it is coming from the real space. Example of real space. But if you look at the complex space, so this is the real space example. Example for the real space. Okay, but now there is an example which I wanted to show where this vector space is belonging to the complex space, right? Same, but coming from the complex space. Now each element will be now a complex number. So again, you can write this x1 as some x1 vector. Of course, there is no problem belonging to Cn. Now it will be the same, but this is x11, x12, so on up to x1n. But they are all complex numbers. Complex numbers. Okay, but now the linear transformation x1, this will now be a linear transformation from Cn to C1. Again, it will be a scalar, but it will be a complex scalar. It's a complex number. Okay, so this is what it is. But when you do it, what it will be? It's nothing but x11 bar, x12 bar, so on up to x1n bar. So this is nothing but x1 which you have written, it's dagger. This is complex conjugate of x1. Complex conjugate of x1, or I would say complex conjugate transpose. Earlier, in case of real, it was only transpose. Now it is a conjugate transpose. So this dagger is a kind of a Hermitian. So this transpose is already written here because this is the actual vector, which is a column vector. Now it is a row vector because of the transpose, and these bars represent conjugate. Okay, that's all. So now if you do it, x1 same, so what will happen? So it will now x11 bar, x12 bar, so on up to x1n bar times the vector, original vector, x12. Somewhat different is there, the notation, and finally the things will conjugate. Alright, so this is how it is defined. So let us do an example, real example of uh, this inner product, but in a complex way. So let us say this x is a vector which is 1 plus I and 1 minus I. Okay, and so this is belong to what? C2. Two elements are there. Similarly, y, another vector, which is a complex, consists of complex scalar, p minus I. Again, this is also belonging to C2. All right. Coming from a same vector space, let us consider. Now, how will we do? So, this x is nothing but this, and this y is nothing but this. But what about this? If I have to calculate this will be what? It will be conjugate transpose of x, right? So how will I do that? Transpose will be, because x is a column vector, now it will be a row vector, but complex conjugate. So conjugate 1 minus I conjugate. So this transpose is there. Now 1 minus I, this will be 1 plus I. Okay, so this is the conjugate, symbol of conjugate. So what you do in the conjugate, just the sign before the iota has to be changed. Okay, so this is what you have. I think, okay, this is 2 minus I. It's like 2. Okay, similarly for y, now it is easy. Again, a row, so it will be 1 plus 2i bar 3 minus I bar, which we can write as 1 minus 2i and 3 plus I. again. So it will be conjugate transpose of Y. Done. So this is now done. So let us now do the calculate the inner products. So let's calculate inner products. Okay, let's calculate the inner products quickly. So everything will be clear now. So x with x, if I do, so what will be? This is the x Brahe notation, 2 plus I, and this will be 1 plus I, 2 minus I. If you do it, it will come out to be 2 plus 5, 7, right? So yes, right, fine. Now next is, this is y with y. This will be 1 minus 2i and 3 plus I. And this will be 1 plus 2i and 3 minus I. So it will be just a plus iota b into a minus iota b. That is a square plus b square. So it will be 5 plus 10, that is 15. Similarly, now if you do x oblique y in a product, then what will happen? This is 1 minus I plus I. That means this is bra x, and this is get y, 1 plus 2i, and 3 minus I. Now, if you carefully do this product, it will come out to be 10 plus 2i. But now, if I do y by x, so what will happen? This will be 1 minus 2i, sorry, 2i, and 3 plus I. And what about the x vector? 1 plus I and 2 minus I. Once you do it, it comes out to be 10 minus 2i. So what we can clearly see that x, y is nothing but yx conjugate, or you can make it dash. So this is also conjugate. Okay, so this is an important property. So the inner product, if it is coming from the complex part, so x oblique y inner product becomes y oblique x star, the conjugate. Fine. So this is another important thing. Two, three important points. That is norm of a vector or the magnitude. So norm of a vector x is denoted as root over x inner product. Similarly, if you write it in the vector term, the root of a dot inner. Okay, so these are different things. Similarly, orthogonality. What is this orthogonality? So you can see that x oblique y should be equal to 0. Similarly, what we have done in the dot product, that a dot b should be equal to 0. So that is theta is 90. Okay, so this, if this is coming, then x and y are orthogonal. That's all. Fine. And yeah, so that is fine. Okay. These are whatever we have seen are the standard scalar products, but there are certain times comes the non-standard scalar products, but they might be legitimate. So non-standard, let me come here, non-standard scalar product. Right. So this is non-standard scalar product. Suppose you have A, B, these are inner products definitely, can be written as like this: A1 B1 plus half A2 B2 plus one third A3 B. So are these legitimate scalar products? Means we generally write it what? A dot B or A oblique B. Standard scalar product will be what? A1 B1 plus A2 B2 plus A3 B2, like that, right? But are these legitimate? These non-standard scalar products? Yes, they are. So you can see that. Say, let us consider another vector C. Okay, so which is nothing but alpha A plus beta B. How we can prove that they are legitimate? So prove that properties of scalar product are valid. Properties of scalar product are true. Okay, so what we are essentially doing is the distributive property, right? This is how we are uh, approaching the problem. Okay, so for the distributive property, we have said that this is supposed to be, and there is another vector D. Okay, so now if I do the scalar product D with C, this is what the fourth property of the scalar product. Okay, so this is the fourth property of scalar products. Just if you look at, it will be very clear. So D over C will be what? So this will be D1 alpha A1 plus beta B1 plus D2 by 2. Same thing, it will be followed. So alpha A1 by 2. Okay, so alpha, you can say that A2 plus beta B2 plus D3 by 3 alpha A3 plus beta B3. All right. So what you can write is that D1, or you can take alpha common. So D1 A1 plus half D2 A2 plus one third D3 A3. Okay. Similarly, plus beta D1 B1 plus half D2 B2 plus one third D3. So you can see that it is quite well valid, that it can be written as alpha BA plus beta BB. So it's legitimate. This is the only property you can prove, that to show that it is legitimate. Also, if you do this A oblique A, you can get A1 square plus 2 half A2 square plus one third A3 square, which is always greater than equal to 0. This is another property. I think this is the second property. Okay, so this is the legitimate scalar product. So to prove that any standard or non-standard scalar product is a legitimate scalar product, you have to use the distributive law as well as the properties of the dot products. Properties of dot products will be N. Okay. Now I just quickly write down the Cauchy inequalities, and then we will go to the linear dependence and independence and the row reduction thing, and how to calculate the rank. So I think these two will be enough to stop for today. Okay. So just quickly writing down the Cauchy Schwarz inequality. So, so it is simple actually. If you look at the dot product thing, that is A dot B is equal to A, B, and cos theta, right? And we know that cos theta will be always less than equal to 1, correct? So, can I write therefore this A dot B, okay, is always less than equal to mod A, mod B? Similarly, now if I just square it, A dot B square will be less than equal to mod A square, mod B square. That's all. This is what the Cauchy-Schwarz inequality represents. Okay, so yeah, so it's essentially dependent on this cos theta one. Okay, now if you have to write it in terms of the inner products, then also you can write like this. So let me see. Yeah. So for the standard products, you can write, say suppose Z1 star Z2 square will always be less than equal to Z1 star Z1 and Z2 star Z2. So this is essentially the inner product part. Or you can write x dagger y mod square is less than x dagger x y dagger y. Essentially representing the same thing. This okay. And finally, if you have to write for the non-standard one, so you can write like this: a oblique b mod square less than mod a oblique a and mod b oblique. So this is the inner product kind of it. So Cauchy-Schwarz inequality exists in all kind of cases, whether it is a standard, non-standard, or in any way you wanted to represent it. Okay, so these are the Cauchy-Schwarz inequality results. And in the assignment, there is a question where you find that this inequality becomes equality. That I will not show right now. Let the students do. After that, I will show during the solving. Okay. Now, half an hour, less than half an hour is left. So let us move to the linear combination of the vectors, and from there we deduce the dependence and independence of the vectors. Okay, fine. So let's jump on to the linear dependence and independence. Okay, so what it is, suppose you have a vector v which has vx as a component, vx hat, vy, vy hat, and this ex and ey are mutually orthogonal. Are orthogonal. Okay, so this is what generally we do, the I cap, j cap, and something like that. Okay, now in any plane, v, this vector, can be written as linear combination of two non-parallel vectors a and b. So your v is nothing but v1 times a plus v2 times b. Okay. Now, how we can segregate this out? That is, how what will be the v1 and what will be the v2? For that, let us do this. V cross a. What you will get? A cross a will be 0. So what will we be? So it will be v2 b cross a. Correct? This we will get. Similarly, v cross b will be v1 a cross b. Now the interesting thing is that if you have two vectors, say A and B, in a same plane, I can define a normal vector, unit vector, I would say, in hat as A cross B, actual vector, divided by the its magnitude. This becomes the unit normal vector. Normal vector from where to the plane. Okay, so these are the normal vectors. Now, what we can do is that, see, A cross B magnitude in hat is nothing but A cross B. The vector. See, I have this A cross B thing. So V cross A, okay, V cross A. Now dot n cap if you do in both sides, if you just multiply with n hat, then I think you will be able to get the actual thing. So suppose this dot n hat you do, and V2 you have B cross A, right? So this B cross A can be written as minus V2 mod A cross B because already an n hat is there, right? So this is how we can write. Okay, so your V2 becomes therefore minus B cross A n hat divided by mod of A cross B. This is one of the representation of V2. Similarly, you can write V1 as V cross B n hat divided by E cross B. Alright, so this is what you can write. Okay, yeah, yes, fine. So, okay, so this is how you can write, and therefore, the actual vector V can be written as therefore that your this is V cross B divided by mod of A cross B, right? N hat into A vector B cross A n hat divided by mod A cross B B. So this is how the linear combination. So V is written as a linear combination of two vectors A and B, right? Now, point is that linear dependence means what? So this linear combination is important for both linear dependence and independence. So in linear dependence, what happens is that your linear combination, if your linear combination is set to zero, is set to zero, then if all coefficients is not equal to zero, when any one coefficient is not equal to zero, or if any one coefficient is not equal to zero, then it is linearly dependent. Okay, linearly dependent. So how we can write? So it is like suppose you have several vectors, 2, 3, and so on. There's many vectors suppose, and I can write this as a1, 1 plus a2, 2, and so on, and that is set equal to 0. And suppose your a1 is not equal to 0, then I can write this one as minus a2 of 2 minus a3 of 3 and so on divided by a1. So you can see that this vector is dependent on other vectors, right? 2, 3, so on. Okay, but now the second part is linearly independent. So it is just the opposite one, independent. Linearly independent means that you have suppose this a1, sorry, a1 1 plus a2 2 and so on, and that is equal to set to 0. If now a1 is equal to a2 is equal to so on is equal to all coefficients, if it is equal to 0, then it is linearly independent. It's not dependent on anything. Okay, so this is the linear independence. Fine. Next, we will go to the last part of today's lecture, which is your row reduction technique, and to find out the rank. So, row reduction and rank of a matrix. two are essentially the same. From the same row reduction technique only, the rank can be found out. I just write first the different techniques to do this row reduction, and then let's take one, two examples to illustrate how to calculate or how to do this row reduction and how to calculate the rank of a matrix. So let us write the rules for row reduction of a matrix. Okay, rules for row reduction. Number one, you can interchange the rows or columns. This is number one. Number two, multiply a row. Okay, this is row reduction, so you don't write the columns. So multiply a row by a non-zero constant. Right. Third, add a multiple of one row to another. This will get clear when we do. Okay. Now, what will happen after doing all these steps? Where you will understand that now you have to stop. So the stopping criteria is that the leading entry of every row is 1. This is important. Number 2, column containing the leading entries of some row must have no non-zero, that means zero entries. So what it tells us is that suppose you have this stopping criteria is this, so 1 0 0 0 1 0 0 0 1, kind of an identity. Not necessarily that here it will be completely zeros. C1 C2 can also come, any number, but this is how the row reduction form looks like. Okay, so this is what essentially it is. Next is the rank of a matrix. So the rank of a matrix is the number of non-zero rows remaining when a matrix is row reduced. Okay, so this is how the rank definition is done. So we will take an example and try to illustrate that how we can calculate the rank of a matrix. So suppose you have been given one example, and once we calculate, we will stop there. Okay, so let us take an example. So x minus 3y minus 4z is equal to 0. We know that we start with linear equations. So 2x minus y plus z is equal to 2, and 4x minus 2y plus 2z is equal to 3. So I can write this as some m times x is equal to r. Alright. So m times x is equal to r, where m is the left hand side numbers 1 minus 3 minus 4, 2 minus 1 1, 4 minus 2 2. X is nothing but simple x y z. Then next r is the right hand side of the equation, that is 0, 2 and 3. Alright, so this is how we can write. Now, how to do the row reduction is now the next question. So let us do what? Let us calculate first. Calculate rank of matrix M. Let us do that first. So what is M? So we start with M like this. So it's 1, 3, 4 with a minus sign. 2 minus 1, 1, 4 minus 2, 2. So the first step is that, let us do one by one. So the first step is that R2 is equal to R2 minus 2R1. See what we need to do. I have to keep here 1, I have to keep 1 here, I have to keep 1 here. All these diagonal elements, I will try to keep 1. And all other elements below or above it has to be 0. That is what the row reduction main role is. So I already have a leading entry over here 1 in the diagonal. Okay, this is 1. All these things needs to be 0. So I have done R2, the second row, minus 2 times R1. So if I do that, 2 minus 2 will be equal to 0. So here it will be 0. Similarly, R3 has 4, so minus 4R1. If I do that, what will happen? See, this becomes 1, 2 minus 2 will be 0, 4 minus 4 will be 0. So I have got one row or one column where the leading entry is 1, all the other columns are zeros. Okay, this is one of the steps. Now you have to follow this for the other columns also. Okay, so first row has nothing to do with here because there's no operations on the first row. Operations are there in the second and third row. So it will be minus 1, R2 is minus 1, minus 2 times R1, that is 6. So minus 1, minus 2, minus 7. Similarly, minus 2, minus 4 times 3, 12. So it's minus 14. Similarly, 1 minus, there is a minus here, plus 4 times 2, that is 8, that is 9, and 2, so this will be 9, this is 2 minus plus 4 times 4, 16, that is 18. So this is how the operations are converted. Next, I want this to be 1. Okay, so for that, what I have to do? Let us do simple. R2 becomes minus 1 by 7 R2. It's as simple as that. So we get 1, 0, 0. Here you will not get anything. 3, 1, minus 14, minus 4, minus 9 by 7, 18. Correct? This is done. The third step. Next, what? Let us do further. Where this has to be 0, this has to be 0. So what to do? R1, that is C, should be equal to R1 minus CR2. Then only it will be 0. And R3 will be R3 plus 14 R2. Let's do. So what will happen? This is 1, 0, 0, 0, 1, 0 directly. There is no problem. But you have to calculate this. Because this will not change. See, uh, R1 if you put 1, R2 is already 0. So it will be always 1. Okay. Let's do the third column. Okay. R1 minus 4 minus 3 times minus 9 by 7. Alright. So it will be then what? Minus 1 by 7. Minus 9 by 7 will be as it is. What about R3? 18 minus or plus 14 into minus 9 by 7. So 7 twos are 14, 9 twos are 18. So it will be 0. Well, I cannot have now 1 over this region. So this is already a row reduced form. And how many rows are there which are non-zero? So this is one and this is another. So the rank of matrix M is equal to 2. That's all. Fine. Similarly, you can have another interesting thing which is called the augmented matrix, generally defined as A. How we can write is M and R. So the writing is like this: one, the original M matrix, 2 minus 1, 1, 4 minus 2, 2, and on the other hand, you have 0, 2, 3. That's all. This is your augmented matrix A. Let's see what is the rank of it. Okay, this is what the question is. What is the rank of it? Okay, so let's see. Again, we have to do the same row reduction. So let us write it. A. So this is A. This is 1, 2, 4. The original matrix. Okay, 3 minus 1 minus 2 minus 4, 1, 2. And over here 0, 2. Operations in the first step is the same as the first what we have done in the first case, and R3 will be equal to R3 minus 4. What it will give? Simple, 1, 0, 0. This gives you, see, these are already being done. 3 minus 7 minus 14. This is minus 4, 9, 18. Now, extra step, this has to be solved. So it is 0 initially, and this will be 2 because this is 0, so this will not change. Okay, is fine. Next step is what? R2 has to be minus 1 by 7 R2 because I need this to be 1. So once you do it, it becomes 1, 0, 0, 3, 1, minus 14, minus 4, 9 by 7 with a minus sign, 18, and 0, 2 by 7 with a minus. Alright, this is the next step. Further, if you go, now same R1 becomes R1 minus R2, R3 becomes R3 plus 14 R2. And once you do that, the second column is prepared. Great. Now you have to do this. This is already we have seen minus 1 by 7, minus 9 by 7 as it is, and this is 0. What about this row? This we have not calculated earlier. So now let's do it. So it is 0. So it will be 0 minus t times minus 2 by 7. So what it will be? Plus 6 by 7. Right? 6 by 7. This is minus 2 by 7 as it is. What about the R3? 3 plus 14 into minus 2 by 7. This is a 4 minus, so minus 4 will be there. It will be minus 1. Okay, so just do one thing. You try to write R3 as minus R3. And yeah, so you prepared 1, 0, 0, 0, 1, 0, minus 1 by 7, minus 9 by 7, 0. This is 6 by 7, this is minus 2 by 7, this is 1. Correct? Further, you can make these zeros. So, easy step, R1 becomes R1 minus 6 by 7, R3, R2 becomes R2 plus 2 by 7, R3. So, 1, 0, 0, 0, 1, 0. This you have to calculate again. But R3 is 0, right? So, you don't need to calculate anything. 9 by 7, this is 0. What about here? 0, 0, 1. So, how many non-zero rows are there? 1, 2, and this is 3. So, rank of A is, see, rank of the augmented matrix becomes 3. Rank of the original matrix, the M, is 2. That's all. So this is how the row reduction has to be performed. It's a lengthy process, but it essentially gives you the rank of a matrix. Okay, so with this, I think we should finish today. So I just give a quick recap of what I have done today. So we started with the vectors. We have seen that mathematically in linear algebra, uh, we need to satisfy many properties like addition, closure, okay, scalar multiplication, distributive, commutative. So many properties are there which a vector must follow, along with the physical property that it should have its magnitude as well as direction. Okay, so all these properties we have discussed, and then we have seen that a set of vectors, how we can call that as a linear vector space only when it goes under the vector addition as well as scalar multiplication. There must be an existence of a unique null vector, and there must be an existence of a unique inverse, additive inverse. And we have done some questions on that. Uh, then we have discussed why, how can we prove that there is a unique null vector and a unique additive inverse for a particular vector in a vector space that we have proved. Then we went to dot product, the vector scalar product. And we have found out that the essential expression is a dot b is equal to ab cos theta. But remember that those vectors should be coincident or coinitial. The angle between them is the cos of that angle. And of course, if these two vectors dot product becomes zero, then we can say that a and b are mutually orthogonal to each other. Now, for a legitimate scalar product, it must follow these four properties. The most important one is this one, and a dot a should be greater than zero. You can also prove this. Okay. Finally, we went to dual vector space. Why? Because sometimes what happens is that every time you don't get a real field, you may get a complex field. To generalize both real as well as complex, we define inner product. And in doing so, you need some kind of a linear transformation. For that, this dual space is important, where we introduce the bra sign. Earlier, vectors are represented by the ket sign. Now, it is a bra sign. So, bra sign is a different thing. It's a linear transformation. It essentially means the linear transformation. And then we look for the inner products. We have taken an example where we have taken a complex field as well as a real field. And we have taken a real kind of mathematical question for the complex field and try to show that what does the get x mean, what is the bra x means, and then calculated the inner product. We found out that inner product of x and y, when it is a complex quantity or coming from the complex field, is nothing but inner product of y and x with a conjugate. Norm of vector is also defined as the inner product, and then we saw the non-standard scalar product, and they are also legitimate by proving these the following laws, the laws which we have seen, that it should be commutative, it should be its own inner product should give you greater than equal to zero, and the distributive property. Then Cauchy-Schwarz inequality, I have just written it down, and then linear dependence and independence. So dependence means linear combination if it is set to zero, one of the coefficients should be non-zero. Linearly independent, all coefficients should be zero when linear combination is set to zero. Then we have seen the row reduction technique and the rank of a matrix. The last step of the row reduction technique, where you stop the row reduction, you see how many rows of this particular matrix is non-zero. That is the number of rank of the matrix, and we have solved it in the question. That's all. So with this, I think today we can end. Okay. So we can see you next Tuesday. Thank you.